Hello everyone, thank you all for being here and spending a wintry evening listening to talks about astrochemistry. So I'll start with a bit of a history lesson, or a recap of Bill's talk as well. During the Big Bang, only hydrogen, helium and a little bit of lithium was formed. Everything else, all the carbon in our bodies, the oxygen in the air, the metals in the projector, were forged in the cores of stars that died a long time ago. And as these stars died, they expelled their life's work back into space, and somehow all these atoms ended up in this configuration, our Earth with us on it. So while Will talked more about how stars and planets are formed and the chemistry that brings life on Earth, I will talk a bit more about what happens when stars die and how you can recycle a star into new stars and planets. So this image shows you the life cycle of a galaxy. Stars are formed from clouds of material that occupy the space in between the stars, and that's called the interstellar medium or the ISM. And the life and death of a star is all determined by its initial mass or its birth weight. And we can distinguish two scenarios. We've got the massive stars and the stars more like our sun. So I'll start a bit more with the massive stars. And these are stars with an initial mass more than 8 to 10 times that of our sun. But actually, before I start with massive stars, I should talk about what I actually mean with like a dying star. So a star is continuously struggling for its life and fighting against gravity. Because gravity is pressing down and wants a star to collapse into one single point. But adult stars, like our sun, they fight against gravity by fusing hydrogen in their core. Because if you smash 4 hydrogen atoms together into one helium atom, which is very difficult to do on Earth, it's super easy if you're a star, you liberate a lot of energy. And this energy is what makes our sun shine, and also provides like a pressure gradient to fight against gravity. So by fusing hydrogen in the core, you can withstand gravity and you live for like another day. But at some point you will run out of hydrogen in your core and then you start to die. So first I'll talk about how massive stars die. When they run out of hydrogen in their core, they will swell up and become red supergiants. And a red supergiant is called like that because, well, it's very red, and also it is more than 100 times the size of the sun. A very famous one is can be found in the constellation of Orion, and you also heard about that one in the quiz, and it's Betelgeuse. So it's the big red blob, well, red star over there. It's a red supergiant. You can see it even from the city center of Leiden on a dark red. So once the red supergiant phase ends, the star will collapse under its own weight. You can't withstand gravity anymore, it's over. And as a result of the collapse, the star will explode as a supernova. And in the supernova explosion, it will expel all of its outer layers and all of its life's work, all the heavy elements forged in its core, back into the interstellar medium. The only thing that's left behind is either a neutron star or a black hole, and that again depends on its initial mass. And a supernova is a very interesting way to die. It really speaks to the imagination, but only a minority of stars dies that way. The vast majority of stars are stars like our sun, and they don't go supernova when they die. They die in a much more gentle manner. So these solar-like stars, once they run out of hydrogen in their core, they will also swell up, but not to the red supergiant level, but rather to the red giant stage, so a few 10 times the size of the sun. And afterwards, rather than going supernova, they will lose their outer layers by means of a gentle outflow. So not Big Bang, well, not a very Big Bang, it's not the Big Bang, but not supernova, a gentle outflow of material. The only thing that's left behind is a white dwarf, and for a very brief period in time, some 10,000 years, it's able to light up all the material that has just been lost and form a beautiful planetary nebula. So as stars die, they eject all of their life's work, all of these heavy elements, back into the interstellar medium and enrich it with heavy elements. So it's a bit like reincarnation, but more of a cumulative reincarnation. You always add more and more heavy elements. And I will now talk a bit more about how stars like our sun die, partly because that's how most stars die, but mostly because that's the topic of my research. So the outflow happens during the asymptotic giant branch phase, or the AGB phase. And that's a very descriptive term if you're an astronomer, but I admit it's not the best term in terms of PR, like supernova definitely has a better ring to it. Nevertheless, during the AGB phase, loads of interesting things happen, and here you have an image in the visible of IRC 10^16 or CW Leo. And this is the most famous AGB star, and you can really see all of the material that's moving away from the star into the ISM. And the bit of outflow that you see here spans some 2000 AU, and an AU, an astronomical unit, is the average distance between our Sun and the Earth. Our solar system is some 100 AU, so this thing is enormous. And in fact, you can't see the star itself because it's hidden by all the material that's being expelled in the outflow. And in particular, it's being hidden by all the dust that's formed in the outflow. And that's really something quite special, because Will already mentioned that chemistry in space, it's not easy if you're a molecule in space. Space is a very hostile environment, and for dust to condense from the gas phase, you have to go through this phase transition, and that's very difficult to do, and AGB outflows are one of the few places in the universe where you can efficiently create loads of dust. They're very efficient dust factories. Right, this is another example of an AGB star, this time in the UV. So we've got Myra. I'll move a bit to the side. So Myra is somewhere over here on the right, blowing a bubble by using its, via its outflow, but it's also moving through the interstellar medium. And as it moves through space, it leaves this tail of material behind, and this tail is about 13 light years beyond. So here you've got an AGB star polluting its environment, caught in the act. And AGB outflows are very rich astrochemical laboratories. They host different types of chemistry, and I will now talk a bit more about what you can find within them. So this is a schematic overview of half an AGB star on the left. And the type of chemistry within the outflow all depends on the elemental carbon to oxygen ratio of the star itself. And this is because of the strong molecular bond of carbon monoxide, CO. If you put carbon and oxygen together, they just won't form carbon monoxide. So all stars start out as oxygen-rich, so they have a C/O ratio that's smaller than 1. You can then assume that all of your carbon is going to be locked up into CO. You will have only oxygen left over, so oxygen-rich chemistry throughout the outflow. Now, during the AGB phase, there's a process that happens within the center, or within the star itself, where carbon that's newly formed through nucleosynthesis is dredged up from the core to the surface. And with each dredge up, you slowly increase the C/O ratio, and after a while, you might become carbon-rich, and you will have a carbon-rich chemistry. Now, our Sun will never become a carbon-rich star, because you need to be massive enough to experience enough dredge-ups to become carbon-rich, so the chemistry within the outflow really depends both on the initial mass of your star as well on the star's age. Now, these AGB stars aren't very well behaved. The outer layers are very convective. So convection is what you have if you have a pot of boiling water. And here you have a simulation of such an AGB star. You see these huge convective bubbles that move up and down in all these different directions, making a bit of a mess as well. So with each convective bubble moving up, you have these pulsations, and these pulsations cause shocks, and the shocks take the chemistry close to the star in the inner wind out of equilibrium. And by that I mean you can break up the very strong CO bond. Now, a bit further out, the density is still high enough and the temperature low enough for dust to condense from the gas phase. The type of dust that you form depends on chemistry. So if you have an oxygen-rich chemistry, you make silicates and metal oxides, so tiny sand grains. If you have a carbon-rich chemistry, you mostly make amorphous carbon, which is basically soot grains. So like it's an enormous combustion engine, a carbon-rich AGB star. And this dust is very critical to launching the outflow, because the dust is opaque to the infrared radiation of our very red star. By that I mean that if an infrared photon hits the dust grain, it absorbs the photon's momentum, so the dust grain will start to accelerate away from the star, and as it moves away from the star, it bumps into the gas, drags it along, and launches the outflow. So the chemical process of dust formation launches the outflow of our star and determines the final phases of in the lives of stars like our sun. So chemistry is what kills off the sun. Finally, in the outermost regions, the material has reached its terminal velocity, and that's between 5 to 25 kilometers per second. And it might sound very fast, but in astronomical terms, it's really just a gentle breeze. And the chemistry in this region is a very rich photochemistry. As you move away from the star, the density decreases. So UV photons from the interstellar radiation field, all the stars surrounding your AGD star, can penetrate this region a bit more easily and create a very reactive soup of molecules, atoms, and ions. So there's a lot of chemistry going on in here. Before I move on, I'd like to point out the size of these things. So the AGD star itself is enormous. The radius of an AGD star is about 1 AU. So this means that our Earth will be swallowed whole by the sun. But there's no need to worry because it's only in 4 billion years and we'll all be dead by then anyway. And this outflow goes from the stellar surface all the way to where it merges with the ISM. And this can range from 20,000 AU. So it's an enormous star surrounded by an even bigger outflow. Because you have this outflow, if you have a decrease in density and temperature, you have these 3 distinct regions all within one object. So AGD stars are very rich astrochemical laboratories, and so 18 out of the 320 molecules that have been detected so far are detected in them. So the story that I've been telling you is very simple. You've got a spherically symmetric star, okay, it's boiling away a bit, whatever, blowing a bubble in space. But of course, it's never quite as easy. Here you have an observation by the ALMA telescope of CO, so carbon monoxide, around our Sculptoris. And that's not a nice bubble. There you clearly see there's a spiral. It's interesting. Another nice example is the disk around L2 puppies. So this is an image taken by the Very Large Telescope. It's optical. And the dark band that you see there is an edge-on dusty disk. So it's a dusty disk that blocks the light, and you did 2 cones of light. Our light is being scattered off this disk. If you look at L2 puppies with ALMA, so a different telescope, you can look at the dust, and you see that there's a blob. And the blob also moves over time, and this blob might be a massive planet, about like a Jupiter mass in size. Now, if you look at more AGD outflows with ALMA, so like a very high resolution telescope, you see that spherically symmetric outflows are the exception rather than the rule. So here again, you've got 12 outflows, oxygen-rich outflows, CO emission, the red is moving away from us, the blue is coming towards us. None of these outflows are spherically symmetric. Some a bit more so than others, so these are a few shows, that's relatively well behaved. Here you have a bipolar outflow, sort of a butterfly. This guy is more of a space rose, and then this star in particular has both a disk and a spiral. So there's so much going on. And we think that these large-scale structures are caused by binary interaction. Because most stars actually have a stellar companion. Our sun is a single star, and well, it's in the minority. But even if you don't have a stellar companion, you might have a massive planetary companion. Like our sun, we might not have a friend star, but we do have a Jupiter orbiting around us. So these stars or massive planets are then massive enough to perturb the outflow and create all these intricate shapes. And this connects the AGD phase to the next evolutionary phase, which is the planetary nebula phase. And it's long been known that these planetary nebula have these wonderful shapes and structures. For example, over here you have the red rectangle, which is a rectangle and not a spherically symmetric thing at all. So these structures might be caused by binary interaction and already shaped, carved within the AGD phase. A planetary nebula is actually quite a strange name for a dying star. And the term comes from William Herschel, who discovered these objects. So in the 1800s, 1700s, 18th century, he used his shiny new telescope and was looking for nebulae, so clouds of gas in the ISM, and he found some weird ones. He called them a curious nebula, or what else to call it, I do not know. And a bit later on, he said that these objects seem to be planets of the starry kind. So the term planetary nebula was born, and even though it's wrong, we still use it. But maybe he wasn't that wrong, because here you have an image, again, the CO of an object with a beautiful name, HD 101584. And this is the outflow of a star that's just left the AGB phase. So you have a white dwarf in the making at the center, and all these funky structures are going on, so you might expect it, yes, it has a stellar companion. And if you then zoom in more than 1,000 times, you see that there's a dusty disk surrounding the white dwarf and its stellar companion. And this dusty disk is very similar in shape and size to the protoplanetary disks that Bill talked about earlier. So protoplanetary disks around protostars, baby stars that are forming baby planets. And these disks surrounding, well, dying stars might be the sites of second generation planet formation. So some stars might be lucky enough to get a second chance at life and have a new family of planets later on. And maybe our sun, well, for our sun's case, maybe Jupiter is massive enough to shape the outflow of the sun in the disk, and maybe that disk is then able to survive the next phases, and maybe our sun will have a next family, a second family. So our Earth will be swallowed whole, but maybe there will be other planets. The life on these planets will look very, very different, because a white dwarf is nothing like a solar-like star. White dwarfs are not as bright, or million times, no, maybe not millions, but thousands of times less bright than the sun, and also they shine most of their energy in the UV, so not in the optical. So life would look very different. And white dwarfs are slowly cooling down as well. It takes a very long time, but cooling down, they go. So after a while, there might be second generation orbiting just the ashes of a dead star. Right. So when you think about how planets and stars are formed from dark clouds that collapse and from protostars surrounded by protoplanetary disks, and then finally you have a star surrounded by a planetary system, you shouldn't forget that this all starts with dying stars that seeds the universe with dust and gas, newly forged elements that form the building blocks of the next generation of stars and planets. And maybe some of these stars can have multiple generations of planets. And I'd like to end my talk with this image, and that was taken by Voyager 1 mission on Valentine's Day of 1990. So right before Voyager left the solar system, we looked back one last time and took a picture of the Earth, in case you can't find the Earth. It's this white dot over there. And this is a group picture of humanity, because everybody who was alive at the time or had already died is in this image, but also everybody who wasn't yet born is there, because all the material necessary for our existence is all within this pale blue dot and brought to us by stars that died a long time ago. Thank you for your attention.
Hi, Matt. Yeah. So, thank you very much for your talk. Super nice. I'm wondering, the point that you were explaining how this carbon-oxygen ratio affects the chemistry. At some point, you talk about dust, but of course, from the quiz, I just learned that silicon is also super important. And how does the silicon come into play? Like, is it inside the star? Is it like, nearby? And what if there isn't any silicon, then what happens?
Okay, thank you. So I'll repeat the question for the people in the back. So the question was about dust formation and where does the silicon come from, if I summarize it. So the star contains, except for carbon and oxygen, it also contains a lot of silicon. And these HB stars are quite cold, they're only 2,000 to 3,000 Kelvin. So in their atmosphere, molecules are able to exist. So SiO, for example, is one of the molecules that float around. But so you have all the building blocks of forming silicates, they're there. But exactly how we actually go from molecules to larger scale clusters to then a solid state dust particle, that we actually don't know. We don't know exactly how dust condenses. We do know that all the building blocks are there, and by comparing observations to chemical models, you can sort of tease out the connections, but all the building blocks are already in the star from like all the stars that died. So that's nice. Yes.
Yeah, I had a little question about the second generation of planets. Are there any ideas how UV-based life could exist? Because we are optical-based, we've got chlorophyll, that sort of stuff. Is there any ideas on how UV-based stuff?
Yeah, I suppose it all depends on whether your planet could hold an atmosphere, because the sun also emits quite a bit in the UV, and our atmosphere is thankfully filters out most of it, because otherwise we would get even more sunburns. So I suppose if you can get a large atmosphere, maybe you would be safe. But otherwise, yeah, that's a very good point. You would be zapped into smaller bits. It would be very unpleasant. Yeah, there's loads of.
Do we, for instance, already know some organisms that use UV light for the energy needs?
Not being like plants, but a little bit. Yeah, that's in the optical, true. But I don't know. Some bits are able, or some, like the little space bears, they're able to exist in space.
Withstand, but not use, right? So
yeah, I don't know. I'm not an astrobiologist, I'm merely an astrochemist. That's a good question. But that is, yeah, that's a very valid point. Yeah, for that you have to look at extreme environments and try and light at things and see if they survive, or maybe you're born. I don't know. That's somebody else. It's for somebody else to play with. I can't do that.
The second generation planets thing sounds super interesting. Is that something that's, you made it sound like kind of a hypothetical. Is that something that's evidence?
So there are some, so second generation is there evidence. There are some planets that have already been detected to orbit around white dwarfs, and that are at a distance to the white dwarf that doesn't make any sense for them to survive the HB phase and so on. So there appear to be some planets that have to be formed through second generation planet formation, and also have these disks around post-HEV stars. They have a very similar structure to protoplanetary disks, and you also have these gaps that are being carved out by maybe planets. So that's something that people are working on, but yeah, it's very new science, because you need a very high resolution telescope to look at those tiny disks very far away. But yeah, people are working on it. And there's some evidence that they exist. Oh, yeah, no, I think, yeah.
Yeah, so these second generation planets, should they be considered brand new, as in coalesce on dust, pebbles, etc., or are they maybe older planets that were in an outer orbit that have migrated upwards?
Yeah. That's a really good question, and it's also sort of feeds into the question of how dust is formed in HEV outflows, because we still don't know how it's formed, we know it's there. But maybe if you take, for example, a rocky planet like the Earth and you just heat it up and evaporate it, you'll already have some building blocks. So, yeah, can you consider it new? I don't know. It's definitely recycled, that's for sure. Maybe you've got some big bits floating around, but it all depends on how much you sort of homogenize the initial planetary system. Or maybe you bump into something like Saturn and you just absorb it as an atmosphere, and then you can have a UV-based life. I don't know.
Yeah, I was just starting to wonder actually, because you were talking about how the outflows and supernova burst that material that can get used to form another star. But I'm wondering, does that material that also go into planets that already exist? Like, what I mean? Like what happens in the places that are already there?
So, if a massive star were to be super close by and go supernova, and B would like absorb some of the elements, I don't think it would be a good time. So unlucky planetary systems might have that, but for example, if Betelgeuse is quite close by and it goes supernova, which is supposed to do in the next few hundred years or so, we will still be safe. It will just be very bright for a bit, but we will still be safe. But yeah, if you're very unlucky, maybe then, but then you need to look at the distribution of stars along the night sky, and that's not something I'm super familiar with. But if you're very unlucky, yes, but we're not that unlucky, so that's good. Yeah, we're safe for a bit.
Would second generation planets be enriched in certain elements?
Yeah, maybe the composition would be very different. Well, there would be more carbon, for example, because carbon is abundantly formed in in AGB outflows, by AGB stars. So yeah, the composition will be a bit different. There will be more heavier elements, but whether that might, for example, have a significant impact on the type of rocks you form on a rocky planet or gaseous giants, that I don't know if it's like that significant. But yeah, maybe after a few goes.
If there are no more questions, thank you very much.